The story of the implosion design begins with a moment of scientific crisis, when the early ideas about how to create a nuclear explosion suddenly proved inadequate. The initial gun-type approach, simple in concept and relatively easy to engineer, had worked for uranium. It relied on shooting two subcritical pieces of material into each other to form a supercritical mass. But when scientists tried to apply the same logic to plutonium, everything changed. Plutonium behaved differently, more unpredictably, more dangerously. It created stray neutrons, threatened premature detonation, and refused to wait for a slow mechanical assembly. This was not a failure of engineering. It was a revelation that the atomic age demanded a completely different way of thinking. The implosion design was born not out of comfort, but out of necessity, pushing science to reinvent itself in real time. The idea of implosion was unlike anything the Manhattan Project had attempted. Instead of bringing two pieces together, the new design would compress a single sphere of plutonium inward with astonishing symmetry. It required a mental leap, a willingness to abandon old mechanical intuition and adopt a vision rooted in the physics of shock waves, high-density states, and precise timing measured in millionths of a second. Nothing in traditional engineering resembled this concept. It was closer to the mathematics of stars, the pressure at the heart of massive celestial bodies, the behavior of matter under conditions far beyond human experience. By embracing implosion, scientists crossed a threshold into forms of knowledge that had barely been explored, transforming theory into a working device through sheer determination and intellectual courage. At the center of this breakthrough was the realization that brute force would not work. A nuclear weapon could not rely on simple impact or speed. Instead, it had to create a perfect inward collapse, a moment when explosives arranged on the outside of a sphere could detonate in such harmony that their shock waves converged at the exact same point. This inward, driving force would compress the plutonium into a super-dense state, increasing the likelihood that each fission event would trigger another. The leap here was not just technical, it was philosophical. It reflected a new understanding that symmetry, timing, and wave dynamics were the true governing forces of nuclear physics. The implosion design transformed the bomb from a clumsy mechanical device into something that resembled a scientific instrument, controlled with extraordinary precision. The challenge was vast. To make implosion possible, scientists had to learn how to shape explosive force the way an artist shapes clay or a physicist manipulates light. Ordinary explosives produced outward shock waves, chaotic and destructive, but the implosion mechanism required shock waves that curved inward with perfect balance. This led to the invention of explosive lenses, arrangements of fast and slow explosives, designed to bend shock fronts, just as optical lenses bend rays of light. The concept alone was bold, but making it work demanded new theories, new manufacturing techniques, and a willingness to reimagine what explosive engineering could accomplish. The genius of this step lay in recognizing that explosives could be used not just for destruction, but for control, precision, and geometry. This reimagining marked a profound shift. The scientists were no longer thinking only about detonation. They were thinking about tempo, rhythm, and choreography. Every part of the device had to fire with perfect synchronization. If one detonator misfired, if one segment produced slightly too much or too little pressure, the entire mechanism would collapse or fizzle. The system required timing circuits that functioned with microscopic accuracy, electrical signals that triggered explosions almost simultaneously across different parts of the sphere. The engineering team had to create new detonators, new measurement systems, and new safety mechanisms because nothing that existed at the time could meet the demands of implosion. The design pushed every field involved physics, chemistry, metallurgy, mathematics to its limit. What made implosion truly revolutionary was the way it unified all these disciplines into a single functioning system. It was not just a physics breakthrough or an engineering triumph. It was the merging of dozens of different forms of expertise into one coherent design. Each piece depended on every other. The shape of the plutonium core influenced the shape of the lenses. The behavior of the lenses influenced the placement of the detonators. The timing of the detonators influenced the internal neutron behavior. The entire device was an interlocking puzzle in which no part could be removed without collapsing the whole design. This level of integration was unheard of at the time, turning the bomb into one of the most complex scientific artifacts ever created. The implosion design also represented a shift in human understanding of energy itself. Before this, the idea of releasing atomic energy was theoretical, something physicists imagined while studying the structure of the atom or the processes that power stars. But the implosion mechanism turned that theoretical potential into a controlled, engineered reality. It brought cosmic forces down into a human-built sphere of metal and explosives. This was not merely a technical advance. It was a moment when humanity realized it could manipulate the deepest laws of nature in a deliberate, structured way. This recognition changed science, politics, and global security forever. Beyond its immediate impact, the implosion design became the foundation for nearly every nuclear weapon developed afterward. Its principles, symmetry, compression, timed detonation, high density assembly, form the basis of modern warheads. Even thermonuclear designs, far more powerful and sophisticated, rely on implosion to trigger their initial stages. The original Fat Man design demonstrated that efficient nuclear detonation required high precision rather than brute strength, and this insight reshaped the strategic and technological landscape of the 20th century. But what truly elevates the implosion design to the level of genius is the human element behind it. The scientists working on it were confronted with moral questions as large as the scientific challenges. They knew that every breakthrough they achieved brought the world closer to a new kind of destructive capability. Yet they also recognized that their work represented some of the most complex and elegant problem-solving in modern history. The tensions, doubts, and debates that surrounded the implosion design gave it a uniquely human dimension. It was a creation built not just from equations and diagrams, but from anxiety, ambition, and the weight of responsibility. In the end, the implosion design stands as one of the greatest intellectual leaps of the 20th century. It redefined what was scientifically possible, pushed technology into uncharted territory, and altered the course of world history. It began as an urgent attempt to solve a problem that threatened to halt the nuclear project, but it became a symbol of the extraordinary heights human reasoning can reach when driven by necessity, creativity, and the relentless pursuit of understanding. The brilliance of the implosion design lies in its core mechanism, symmetrical inward compression, a method that redefined what it meant to unleash nuclear energy with control and precision. Unlike traditional explosive devices that rely on force pushing outward, the implosion concept inverted the entire logic of detonation. It demanded that energy be shaped inward, focused like a collapsing star, squeezing the plutonium core until its atoms were forced into a state where a chain reaction could ignite. This inward journey of force required more than raw power. It demanded perfect harmony. The compression had to be even across every point of the sphere, with no distortions, no early spikes of pressure, no delays in timing. It was an engineering ballet happening within microseconds, choreographed with a level of precision humanity had never attempted before. Plutonium itself imposed this extreme requirement. Its behavior made symmetrical compression not just important, but absolutely essential. In its normal metallic state, plutonium's atoms are scattered through a crystalline structure that resists predictable shaping. It can shift phases, expand, or shrink with temperature or minor impurities. Under conventional explosive pressure, plutonium would deform unevenly, creating pockets of density that could lead to a partial or failed detonation. If the core compressed unevenly, one side might reach criticality before the other, producing a low-energy fizzle rather than a full nuclear explosion. This meant that for implosion to work, every inch of the core had to experience identical pressure at the exact same instant. The team had to find a way to turn chaos into symmetry. To achieve this, engineers developed the concept of Hayek's explosive lenses, devices that shaped shock waves the same way glass lenses shape beams of light. These lenses used alternating layers of fast and slow explosives, each arranged with geometric precision. When detonated, the shock wave would pass through the fast explosive quickly and through the slow explosive more gradually, curving the wave front so that it bent inward. The effect was a spherical, inward, moving shell of pressure, converging at the center with exquisite symmetry. It was like sculpting force itself, guiding it into a near-perfect geometric collapse. This innovation transformed explosives into tools of precision rather than instruments of destruction, a profound shift in the science of detonation. Yet shaping shock waves was only the beginning. Timing was the invisible master of the implosion process. Dozens of detonators had to fire simultaneously, each sending its spark into the explosive layers at precisely the same moment. Even a microsecond of delay from one detonator would distort the inward pressure, damaging the symmetry and threatening the entire operation. The scientists developed advanced timing circuits, new wiring methods, and improved detonators, all designed to reduce timing error to an unimaginable degree. What made this achievement extraordinary was the era in which it happened, long before the existence of modern computers and precision electronics. Everything had to be tested, refined, and re-engineered through sheer ingenuity. As the symmetrical shock waves raced inward, they compressed the plutonium core from all directions. At first, the metal resisted, fighting the pressure like any ordinary solid. But as the shock front continued to move inward, the core began to shrink, its atoms squeezed closer together. This change in density was the key. For a nuclear chain reaction to occur, enough plutonium atoms must be packed tightly enough so that when one fissions and releases neutrons, that neutron strikes another plutonium nucleus before escaping. Without symmetrical compression, the atoms remain too far apart to sustain a full chain reaction. But under the crushing symmetry of implosion, the core entered a new state, supercritical, dense enough for the reaction to grow exponentially. Even inside this intense process, symmetry remained essential. The inward compression had to last just long enough to allow the reaction to build. If the sphere cracked or bulged, the reaction would weaken. To ensure stability, scientists added tamper layers, dense materials that surrounded the core, holding it together during the critical microseconds of compression. These layers helped reflect neutrons back into the core, further increasing the efficiency of the reaction. The entire process was a race between the core's expansion due to heat and the explosive shock holding it together, and that delicate balance was only achievable through perfect symmetry. The implosion design's reliance on symmetrical compression represented a new understanding of nuclear physics. It emphasized that the power of a nuclear explosion does not come from the explosive material alone, but from the exact conditions in which that material is transformed. Symmetry, density, timing, these were the real sources of power. The weapon was not simply a collection of parts. It was a system that required unity, precision, and a design philosophy where every component served the larger purpose of achieving inward compression. The wartime urgency added another dimension to the challenge. The scientists were racing under enormous pressure, knowing that failure could change the course of the war and perhaps the world. Despite this, they pushed forward, refining theories, testing prototypes, conducting countless experiments with shock waves and metal spheres. Many of these early tests ended in failure, crumpled spheres, distorted wave patterns, detonators firing out of sync. But each failure taught the team something new about how to control the invisible forces at play. Their progress was not just scientific, it was creative, a process of learning to speak the language of shock, pressure, and symmetry. What emerged from this labor was not simply a bomb, but a new scientific capability. By learning how to generate symmetrical inward compression, the Manhattan Project teams unlocked a principle that would shape all future nuclear weapon designs. The efficiency, compactness, and raw power achievable through implosion became the standard for modern warheads. The method allowed smaller amounts of nuclear material to produce far greater effects, and it provided the triggering mechanism for the even more powerful thermonuclear weapons that would later define the Cold War. But beyond geopolitics and war, the breakthrough in symmetrical compression also influenced scientific thinking. It demonstrated that by understanding how force can be controlled at microscopic timescales and precise geometries, humanity could manipulate matter in ways previously thought impossible. It showed that physics was not just a tool for explaining stars or atoms, but a means of engineering new states of matter through carefully guided processes. The implosion design remains one of the clearest examples of how human intellect can bend nature's deepest forces to its will. It began with an impossible challenge, evolved through relentless experimentation, and culminated in a design that had no precedent in human history. Symmetrical inward compression was not just a mechanism, it was a testament to the power of precision, the necessity of creativity, and the profound responsibility that accompanies any break. Capable of reshaping the world, the concept of Hayek's explosive lenses was one of the most daring and imaginative breakthroughs of the entire implosion program. It required scientists to think about explosives in a completely new way, not as blunt instruments of destruction, but as tools that could shape force with elegance and mathematical precision. Ordinary explosives produce chaos, jagged shock waves, uneven expansion, unpredictable distortions. But the implosion design demanded the exact opposite. It required explosive energy to move like a perfectly synchronized inward, bending sphere, converging at the center of the device with flawless symmetry. Hayek's explosive lenses were the key to making this transformation possible, turning raw chemical energy into a controlled wave, engineered with the deliberate care of a sculptor shaping marble. These lenses were not physical glass lenses, but arrangements of explosive materials layered in specific patterns to bend shock waves inward, exactly as a curved optical lens bends light. The challenge began with a simple realization. If you detonate explosives around a spherical core, the shock wave will not automatically converge in perfect form. Even tiny irregularities, asymmetries, and timing differences cause the wave front to warp. Instead of forming a smooth inward curve, the wave might buckle or ripple. This small distortion would then magnify as it approached the center, ultimately leading to uneven compression of the plutonium. Uneven compression meant failure, because only a uniform squeeze could elevate the plutonium to the density required for a sustained chain reaction. This problem forced the engineers to abandon all conventional assumptions about how explosives behave. They needed to control the wave itself, shaping it with intention. The idea of explosive lenses came from a conceptual leap. If you could make one explosive burn faster and another slower, their interaction could redirect the flow of force. Fast explosives produce shock waves quickly, racing outward at higher velocities. Slow explosives burn at a steadier, more controlled pace. By arranging these materials in alternating layers, with precise geometric curves shaping each boundary, scientists discovered that they could bend shock waves inward. It was the same principle as refraction, the phenomenon where a beam of light entering water bends because the speed of light changes in different mediums. Here, the mediums were not glass or water, but high-energy chemicals engineered to produce different wave speeds. Instead of light, the energy being manipulated was a spherical shock front. Creating these lenses required extraordinary experimentation. Simply placing explosives together was not enough. The boundaries between the fast and slow layers had to be machined with extreme precision, because any roughness, misalignment, or air pocket would distort the wave. The geometry of each segment had to be calculated with precise mathematical formulas, taking into account the speed of the shock wave, the thickness of each layer, and the overall curvature needed to create the final spherical inward collapse. The engineers had to test countless combinations of materials, shapes, and configurations to discover which patterns produced the desired result. They used metal spheres, pressure gauges, heists, bead photography, and new diagnostic tools to measure how shock fronts behaved. These tests, often destructive and unpredictable, built the foundation for understanding how to control explosive force at a level far beyond anything previously attempted. At the heart of the design was a bright simplicity that belied its technical difficulty. When detonators fired across the outer shell, each lens segment would convert a messy outward blast into a carefully guided inward wave. The slow explosive layers delayed certain parts of the wave front just enough for the faster layers to catch up, reshaping the explosion into an inward, curving form. As all segments fired together, these curved waves merged into a smooth, spherical shell of pressure. This shell moved inward like a collapsing bubble, gaining strength and uniformity as it traveled. When it finally struck the plutonium core, it pressed from every direction at once. The uniformity of this pressure was essential, because even slight variations could cause the core to distort rather than compress symmetrically. One of the most remarkable aspects of the lens system was the way it embodied the marriage of physics and craftsmanship. The scientists understood the mathematical behavior of shock waves, but the engineers had to turn these equations into physical objects. Each lens segment had to be manufactured with exquisite care, shaped by hand and machine to tolerances that were nearly unheard of at the time. The room for error was almost non-existent. A lens that was too thick or too thin by even a fraction of an inch could ruin the symmetry. A surface that was not polished correctly could scatter the wave. Every piece of the device had to be identical, carefully inspected, and meticulously aligned. The implosion mechanism depended not only on theory, but on human precision. Timing was another critical element in the success of explosive lenses. Even if the lenses were perfect, they would fail if the detonators firing them were not perfectly synchronized. Scientists developed new types of detonators, fast, reliable, electrically triggered devices capable of firing within microseconds of each other. These detonators had to be arranged with equal distance from the core, and the timing circuits had to distribute electrical impulses with consistent speed. The explosive lenses and detonators worked in unison. The lenses shaped the shock waves, and the detonators provided the rhythm that synchronized the entire implosion. The break-through significance of explosive lenses extended far beyond the immediate wartime project. They represented a conceptual revolution in explosive engineering. Prior to this, explosives were used to break things apart, to shatter, demolish, disperse. The implosion lens system turned them into a medium for delicate manipulation. It revealed that even violent energy could be sculpted into predictable forms if understood deeply enough. This understanding laid the groundwork for later advances in nuclear weapons, high-pressure physics, and shock compression research used in laboratories around the world. The methods used to study shock waves in the implosion program eventually contributed to scientific fields such as inertial confinement fusion, where lasers compress tiny fuel pellets with similar symmetrical precision. The lenses also demonstrated something profound about human creativity in moments of extreme challenge. Faced with a problem that seemed unsolvable, how to force a chaotic explosion to behave almost artistically, scientists pushed their thinking into new territories. They borrowed ideas from optics, adapted concepts from physics, and experimented relentlessly. Their persistence transformed a theoretical idea into a working mechanism. The invention of explosive lenses stands as a testament to imagination under pressure, a reminder that innovation often emerges when the stakes are highest and the rules are unclear. Ultimately, the explosive lenses served as the guiding hands that shaped the implosion, transforming raw explosive force into an inward, moving wave of precision. Without them, symmetrical compression would have been impossible. Without symmetrical compression, the plutonium core could never reach supercritical density. And without that density, the implosion design could not function. The lenses were the quiet triumph at the heart of the device, a fusion of theory, geometry, material science, and human skill. They remain one of the most extraordinary achievements of the project, a moment when explosive force was transformed from chaos into command, and when science proved that even the most violent energies could be shaped with elegance and intention. Plutonium was both the miracle and the menace of the implosion project, a material that offered extraordinary nuclear potential but carried within itself a set of challenges so profound that they reshaped the entire direction of atomic weapons development. To understand why the implosion design became such a revolutionary breakthrough, one must first understand the nature of plutonium itself, its unpredictability, its temperamental internal structure, its dangerous isotopic impurities, and the relentless spontaneous fission events that made traditional weapon designs impossible. The fourth keynote captures all these deeply intertwined scientific struggles, the moments when plutonium defied expectations, ignored predictions, and forced the Manhattan Project scientists to think in ways that had never been required in the history of engineering. The story of plutonium's challenges is the story of the implosion design's necessity, the invisible pressure that pushed scientists toward innovation they never imagined themselves capable of achieving. In the early days, when uranium bombs seemed straightforward enough, plutonium appeared at first to be its cooperative cousin, another fissile material with enormous potential. But as research deepened, plutonium revealed its volatile personality. Unlike uranium, plutonium could not be trusted. Its atoms did not sit in regular, predictable crystal structures. Instead, Plutonium could shift suddenly between multiple phases like a metal that changed identity depending on its mood. Temperature, pressure, or even tiny impurities could force it out of one phase and into another, causing cracks, distortions, or worst of all, irregular densities inside the core. The scientists realized that they were dealing with a material that refused to behave like an ordinary element. It expanded when most metals contracted when others expanded, and warped under stresses that seemed trivial. Trying to shape plutonium was like trying to carve a sculpture out of living clay that could change its properties without warning. This instability made machining plutonium into a precise spherical core extraordinarily difficult. A nuclear weapon required perfection, not an approximate sphere, not something close enough, but something with near-absolute symmetry. Any uneven distribution of mass could disrupt the implosion's final stage. Yet plutonium resisted symmetry. When the scientists shaped it, polished it, or heated it even slightly, the metal would unpredictably transform from one crystalline phase to another, swelling or shrinking in ways that distorted. The sphere, a shape made at one temperature, would be imperfect at another. The challenge was not simply to build a sphere, but to tame a material that acted as though it was alive with its own internal tensions. And this was only the beginning of plutonium's defiance. Inside the metal, deep at the atomic level, spontaneous fission events were constantly occurring. Unlike uranium, which remained mostly quiet until triggered, plutonium was full of microscopic fireworks. It emitted stray neutrons at random intervals, unpredictable and unstoppable. These stray neutrons were harmless during storage, but inside a weapon design like the gun-type mechanism, where fissile material slowly assembled into a supercritical mass, they became catastrophic. A stray neutron could arrive too early, sparking a chain reaction before the assembly was complete. This premature initiation would cause the weapon to blow apart at low yield, a failure known as fizzle. When the scientists ran calculations for plutonium's spontaneous fission rate, the conclusion was unavoidable and devastating. A gun-type plutonium bomb was impossible. The conventional design that worked for uranium would never work for plutonium. This realization hit the Manhattan Project with the force of a scientific earthquake. A massive industrial infrastructure at Hanford was producing plutonium at enormous cost, only for scientists to discover that the material could not be used in the only bomb design that existed. The team faced a crisis not just of physics, but of strategy. They needed a solution that ensured plutonium reached supercriticality faster than stray neutrons could spoil the reaction. They needed assembly at a speed far greater than the gun mechanism could deliver. They needed a way to compress plutonium so rapidly and uniformly that spontaneous fission no longer mattered. Every scientist understood the stakes. Without a new idea, plutonium would become useless for weapon construction. Years of work, billions of dollars, and strategic wartime plans would collapse. The implosion concept was the only path forward. Only implosion could assemble the plutonium core in millionths of a second, far faster than a stray neutron could interfere. But for implosion to work, plutonium itself had to be controlled. Its physical phases had to be stabilized. Its spontaneous neutron emissions had to be accounted for. Its impurities, particularly the plutonium-2, 140 isotope, had to be studied with new urgency. Plutonium-2, 140, was the main culprit behind the elevated spontaneous fission rate. Unfortunately, it was also an unavoidable byproduct of the nuclear reactors where plutonium was produced. Even small increases in this isotope caused enormous increases in neutron emissions. There was no way to eliminate Pu-240 entirely, so the weapon design had to adapt. The scientists needed a core and compression system so fast, so uniform, so overwhelmingly precise that the chaotic internal noise of plutonium no longer mattered. The first step to mastering plutonium was understanding its phases. The metal had at least 6 known crystalline structures, each with different volume and density. The most troublesome was the alpha phase, which was brittle, irregular, and prone to deformation. This phase made machining nearly impossible. But scientists discovered that by alloying plutonium with a small amount of gallium, they could force it into a more workable phase, the delta phase, which remained stable at room temperature. This was a critical breakthrough. Delta phase plutonium allowed the core to be machined into a near-perfect sphere, something previously thought impossible. But even with gallium, plutonium remained temperamental. It required controlled temperatures, careful handling, and precise machining techniques that had to be invented specifically for the project. The second obstacle was dealing with plutonium's internal neutron behavior. Spontaneous fission could not be stopped, but it could be managed. The solution was to incorporate a neutron initiator, an ingenious device at the center of the core that emitted a burst of neutrons at exactly the right moment. Instead of relying on random internal neutrons to trigger the chain reaction, the designers created a controlled source. This ensured that the nuclear reaction began only after the core reached maximum compression. The initiator had to be perfectly timed. Firing too early would ruin the core. Firing too late would allow the core to expand before the reaction strengthened. This tiny device became one of the most delicate and critical components of the implosion system. The third major challenge was the plutonium itself becoming unstable if heated too quickly during implosion. Compressing plutonium generates enormous heat in microseconds. That heat pushes the metal toward other crystalline phases, causing momentary shifts in density. The designers had to predict and control these transitions, calculating how the metal would behave during the shock wave's passage. These calculations required new equations, new models of metal behavior under extreme pressure, and new ways of measuring microscopic distortions in experimental test spheres. The scientists were inventing a new science, high-energy plutonium metallurgy. Then came the problem of isotopic impurities. Plutonium from wartime reactors was never pure Pu-239. It always contained Pu-240 and sometimes other isotopes in smaller amounts. The mixture varied depending on reactor conditions, neutron flux, and fuel burnup rate. This meant every batch of plutonium behaved slightly differently. No two cores were identical. The implosion design had to be robust enough to accommodate this variability, maintaining symmetry under conditions where the exact neutron background of each core could differ. This variability required the designers to create margins of safety within the implosion sequence, ensuring the weapon would function reliably even if spontaneous fission spikes occurred at the worst possible time. To test these ideas, scientists built countless mock-up cores, using non-radioactive metals that mimicked plutonium's density. They blasted these spheres with explosives to measure how compression waves moved through them. They added sensors to map distortions, used HICE, bead photography to capture the microsecond collapse, and built new diagnostic instruments solely for this purpose. Over months of experiments, they learned to read compression patterns like a language, each ripple, each distortion, each asymmetry telling a story about forces inside the core. Every mistake taught them something new about the metal they were trying to command. the scientists gradually realized that the core's geometry mattered just as much as its metallurgy. A perfect sphere was essential, not only for symmetry, but for even neutron distribution. If the core were slightly flattened, slightly elongated, or slightly off-center, the implosion wave would travel unevenly through it. This uneven travel would produce incorrect density regions, causing the chain reaction to stall. Every nanometer mattered. The machining teams created new tools capable of achieving tolerances unheard of in ordinary engineering tools that could measure and polish the metal to near-atomic precision. Even then, the danger of premature detonation loomed. A stray neutron could still trigger the chain reaction too early, before the core reached its ideal density. To counter this, the entire implosion system had to operate at extreme speed. The shock wave had to travel inward faster than any stray neutron could ruin the sequence. The detonators had to fire so simultaneously that the core would begin compressing uniformly before neutrons could act chaotically. All these requirements linked back to plutonium's fundamental problem, its impatience. It simply would not wait for a slow assembly. It did not tolerate delays. It demanded a design that could outrun its own internal physics. As the months passed, the scientists grew more intimate with plutonium's personality. They learned how it behaved under pressure, how it cracked, how it melted, how it shifted, how it emitted particles. They studied its weaknesses and strengths, its hidden temperings, and its strange multi-phase nature. Plutonium became less of an element and more of a creature, volatile, reactive, dangerous, but capable of extraordinary performance if handled with respect and precision. The metallurgists, chemists, and physicists all developed an almost personal relationship with the metal, learning to predict its quirks and coax it into stability. This human element, the quiet dedication of scientists wrestling with a material that challenged them at every step, became one of the most compelling parts of the implosion design story. The key insight that emerged from all this struggle was simple but profound. Plutonium could only be controlled through unity of design. No single innovation, neutron initiators, delta phase stabilization, precision machining, timing circuits, or explosive lenses, could alone solve the problem. It was the interdependence of all these solutions that made implosion possible. Each one compensated for a flaw. Each one supported another. The system worked only when every weakness of plutonium was accounted for and countered by a corresponding strength in the weapon's design. In this sense, plutonium forced the scientists to create the most integrated engineering design of the era. The material's unpredictable behavior shaped the entire weapon from the inside out. It dictated the use of explosive lenses. It demanded synchronized detonators. It required neutron timing. It demanded a tamper. It required a reflector. It required a stable phase. It demanded new machining techniques, new mathematical modeling, and new instrumentation for testing. Plutonium's challenges, in effect, created the implosion design. Every innovation that defined the Fat Man bomb was born directly from the need to conquer the internal physics of this extraordinary element. This was not merely a scientific struggle, but a conceptual revolution, a moment when scientists were forced to rethink what materials could do, what engineering required, and what physics demanded. Under the most extreme conditions ever attempted by human hands, the deeper one looks into the evolution of the implosion design, the more evident it becomes that its success was not simply a matter of physics or engineering, but a profound triumph of human adaptability. The challenges surrounding the weapon's core, the lenses, the timing system, and the compression dynamics were so immense that the scientists were constantly forced to abandon old assumptions and reinvent solutions from the ground up. It was not enough to rely on theory. Every breakthrough demanded new experiments, new insights, and new intuitions. This process of adaptation, of confronting unknowns and reshaping one's understanding, forms one of the most defining chapters in the story of the implosion device. As scientists observed early tests failing to behave as calculations predicted, they saw how the atomic world resisted simple explanation. Metals did not compress evenly, shockwaves did not maintain their symmetry, detonators did not fire with the universality that theory assumed. Every deviation was a reminder that nature did not yield easily to human plans, but instead of halting progress, these setbacks became stepping stones. Teams modified their methods, refined their instruments, and questioned previous models. The development of the Fat Man design thus became a living demonstration of scientific adaptability, a journey shaped by unpredictability rather than certainty. One of the most significant transformations occurred in the understanding of explosive lenses. Early concepts assumed that explosives could be shaped and layered like optical glass, guiding the shockwave with predictable precision. Yet, when experiments began, the shock fronts behaved erratically, bending in unexpected directions, forming distortions instead of uniform compression. Scientists had to adapt by studying how different explosive materials interacted with each other, how subtle changes in density or chemical composition altered the shockwave, and how even the curvature of an explosive block could mean the difference between success and failure. What began as a simplified analogy to light waves evolved into a complex exploration of hydrodynamics, forcing researchers to rethink their assumptions repeatedly. The same pattern emerged with timing. Detonators were supposed to offer simultaneous initiation, but they never did, not at first. The differences were often measured in microseconds, yet even the smallest delay meant an uneven collapse of the core. Instead of viewing these inconsistencies as flaws, scientists adapted by inventing new detonator types, introducing electrical enhancements, and conducting vast numbers of timing tests. Every misfire became a clue that pointed toward improved designs. The development of the explosive bridgewire detonator was not merely a technological upgrade. It was the result of a mindset that embraced trial, error, and refinement as essential parts of the process. In metallurgy, the need for adaptability was even more dramatic. Plutonium behaved unlike any metal they had studied. Its phases shifted suddenly with temperature changes. It expanded when heated and shrank unpredictably under pressure. No previous knowledge from conventional materials could be applied directly. Scientists were forced to explore unknown metallurgical territory. They experimented with alloying, heating, cooling, machining, and shaping. Entire workshops were built specifically to handle this new substance, and new safety protocols emerged as they learned how reactive and temperamental it could be. The adaptation was not only scientific but cultural, changing the very way laboratories operated and reshaping the team's daily routines. The shaping of the plutonium core also required new levels of precision. The team initially believed that a sphere could be machined with standard tools, yet the slightest imperfection disrupted the symmetry necessary for a successful implosion. They developed new machining methods, new measurement techniques, and new inspection standards. Human intuition alone was no longer enough. They needed technologies to measure imperfections on scales previously irrelevant to engineering. The process transformed the nature of craftsmanship, blending human skill with scientific instrumentation in a way that had never been attempted before. Adaptability also shaped the theoretical side of the project. Many ideas that seemed promising in the beginning had to be discarded once real-world conditions exposed their limitations. Simplified models could not account for the turbulent flow of compressing metals, the nonlinear behavior of shock waves, or the unpredictable transitions of plutonium phases. Theoretical teams had to rework their equations, build new models, and create entirely new mathematical tools to explain what experiments revealed. This interplay between theory and experiment, constantly resetting itself, became one of the defining features of the implosion program. Even the organizational structure adapted as knowledge grew. What began as separate teams, physicists, chemists, machinists, explosive experts, eventually transformed into a tightly integrated operation. Communication channels changed, workshops moved closer to laboratories, and specialists began working side by side. The boundaries between disciplines blurred because the implosion design demanded collaboration unlike anything seen before. Adjustments were made at every level, from the highest theoretical discussions to the smallest mechanical details. The project became a living organism in which each part responded to the challenges and discoveries of the others. Adaptability was also visible in the way scientists approached failure. Instead of viewing unexpected results as setbacks, they treated them as essential data points. Failed lens tests, asymmetric shock waves, unstable plutonium samples, all were studied with careful attention. Each failure revealed something that theory had overlooked or something that instrumentation had not yet captured. This willingness to embrace uncertainty and use it as a guide allowed the team to move forward faster than if they had simply adhered to initial assumptions. In many ways, the implosion design advanced not because the team avoided mistakes, but because they learned to interpret mistakes as messages from the natural world. Human adaptability extended beyond the laboratory. The massive scale of the project required logistical improvisation, securing materials that had never been produced in large quantities, building new facilities in remote areas, training personnel to handle unknown substances, and organizing supply chains under unprecedented secrecy. Every logistical obstacle forced administrators and engineers to innovate. The entire system around the research adapted because the science demanded it. The emotional adaptability of the scientists played a quiet but essential role. Many of them entered the project with theoretical backgrounds, unfamiliar with the harsh realities of wartime urgency. They struggled with moral questions, personal exhaustion, and the weight of responsibility. Yet they adapted to new pressures, new environments, and new expectations. Their capacity to remain focused while facing uncertainties, scientific, personal, and ethical, underscored the human element behind the design. The implosion device was not only a technical achievement, but also a testament to human resilience in the face of overwhelming complexity. As the project approached its final stages, adaptability reached its peak during full-scale testing. When small-scale tests suggested unexpected behavior, components were redesigned rapidly. When timing systems showed slight deviations, they were recalibrated overnight. Decisions had to be made quickly, and the team adjusted with remarkable agility. The culmination of this process, the Trinity test, represented the ultimate demonstration of adaptability, a device born from countless revisions, reconsiderations, and reinventions, all brought together in a moment of extraordinary precision. The genius of the implosion design was not only in its physics, but in the human capacity to confront the unknown and reshape understanding again and again. The story of the fifth keynote reveals how adaptability transformed the implosion project from a theoretical challenge into a functional reality. It shows that scientific progress is rarely a straight line. It is a landscape of evolving ideas, informed by curiosity, corrected by failure, and guided by the willingness to change. In the end, the implosion design stands as a powerful reminder that the greatest breakthroughs emerge not from certainty, but from the courage to navigate uncertainty with flexibility, discipline, and an open mind. The legacy of the implosion design is not simply the story of a technological achievement, nor is it contained in the weapon that emerged from it. Its legacy lies in the way it reshaped humanity's understanding of knowledge, responsibility, and the fragile balance between creation and destruction. The implosion design brought into the world a new kind of power, a power so vast and immediate that it forced people to rethink nearly everything they believed about science, war, politics, and the future of civilization. When that device first proved itself, it marked a turning point after which the world could not return to the mindset that existed before. Its legacy became a continuous presence, influencing generations long after the moment of its creation. The scientists who worked on the project often entered the effort with a sense of intellectual excitement. They were exploring the deepest structures of matter, unraveling the secrets of energy hidden inside the atom, pushing physics into places no one had ever reached. But as the implosion design became real, as calculations transformed into metal casings and intricate detonators, they began to feel the weight of what they were bringing into existence. The legacy began there, in the recognition that pure knowledge could no longer be separated from its consequences. The breakthrough revealed that the boundary between scientific discovery and moral responsibility had blurred. This awareness would echo through every major scientific advancement that followed. When the first test lit up the distant horizon, it marked a moment of irreversible transformation. The flash revealed more than a physical explosion. It revealed the arrival of a new era. Those who witnessed it felt a mixture of pride and dread. In that radiance, they saw humanity's ability to unlock the deepest forces of nature, but they also saw the possibility that those forces might one day be turned back against humanity itself. The legacy of that moment became a warning embedded in history, that human ingenuity, when elevated to extraordinary levels, demands extraordinary caution. As the world learned of the weapon's existence, global politics shifted in ways no previous technology had ever caused. Nations realized that their destinies were now intertwined through a new and terrifying balance. Power was no longer determined by the size of armies or the experience of generals. It was now shaped by scientific capability, industrial strength, and the ability to harness the atom. A new strategic landscape emerged, shaped by deterrence, fear, and fragile stability. The legacy of the implosion design carved itself into international relations, ensuring that diplomacy, conflict, and negotiation would forever be influenced by the knowledge that one device could alter the course of history in an instant. Beyond politics, the design transformed the emotional and psychological life of societies around the world. Ordinary people, far removed from laboratories and government offices, began to understand that their fate could be determined by technologies they would never see, by decisions made in distant rooms, by forces invisible yet overwhelmingly powerful. The idea that human civilization possessed the means to destroy itself became part of the collective consciousness. This awareness seeped into literature, films, philosophy, and even daily conversation. It created new anxieties, but also new reflections on what it meant to live in a world where humanity's greatest danger came from itself. Within the scientific community, the legacy took on a more introspective form. The implosion design changed how scientists viewed their own work. It pushed them to consider not only what they could create, but what they should create. It forced them to confront the possibility that certain breakthroughs might carry risks too great to ignore. Entire fields of ethics grew alongside fields of physics, reminding future generations that discovery must be matched with reflection. Laboratories and universities began to incorporate questions of responsibility into their cultures, acknowledging that science could not be isolated from the society it served. The design also reshaped the structure of scientific research itself. The scale of the project demonstrated that massive, coordinated efforts involving diverse experts could achieve results impossible for individuals working alone. This inspired new models for scientific collaboration. Space exploration, advanced computing, and particle physics would later follow the pattern established by the teams who built the Implosion device. The legacy of the design thus extended into the organization of modern science, influencing how humanity tackles its most complex challenges. Yet the most enduring part of the legacy was philosophical. It changed humanity's relationship with power. Before the device existed, destruction on a global scale belonged to natural disasters or divine myths. After its creation, global destruction became something humanity could inflict upon itself. This realization altered the way people thought about progress. The belief that technological advancement always led toward improvement was replaced with a more cautious understanding that progress could also lead toward danger. Optimism became intertwined with fear, ambition with restraint, curiosity with responsibility. The Implosion design also fostered a new sense of global identity. People began to see themselves not merely as members of individual nations, but as participants in a shared planetary fate. The world became smaller, and its survival became a collective concern. The awareness that one nation's actions could affect all others encouraged conversations about cooperation, disarmament, and the need for unity in the face of existential risks. Although these discussions were often difficult and imperfect, they reflected the beginning of a global consciousness shaped directly by the lessons of the nuclear age. For those who built the device, the legacy was deeply personal. Many spent the rest of their lives grappling with the knowledge that their work had changed the world in ways both remarkable and troubling. Some felt pride in having helped end a devastating war. Others felt lifelong guilt. Many felt both. Their internal conflicts became symbols of the broader human struggle to balance innovation with morality. Their reflections would inspire future generations to think more carefully about the consequences of their ambitions. As time passed, the Implosion device itself became a relic, but its influence remained. Every debate about advanced technology, every discussion about global security, every reflection on humanity's future holds echoes of the moment when the Implosion design first appeared. Its legacy shaped the way people evaluate risks, envision possibilities, and confront the ethical dimensions of discovery. It stands as a reminder that human beings possess extraordinary power, and that power must be matched with wisdom. In the end, the legacy of the Implosion design is not defined by the weapon it produced, but by the questions it left behind. It asks humanity to consider what kind of future it wants to create, what responsibilities come with knowledge, and how progress can be guided without sacrificing safety or conscience. These questions remain alive, shaping decisions every day, echoing through modern science and international affairs, reminding the world that brilliance without reflection can become its own undoing. And so the legacy endures, not as a moment in the past, but as an ongoing challenge to the future.